Okay. So what does it mean by geosynchronous orbit, right? It means that if I'm standing on Earth, let's say we're looking from the polar axis down, right? And I'm standing at the equator. This is at the equator. So it's a top-down picture of the Earth. Okay. Now, what it means is that we travel around the Earth we travel around space together, which means that when we come to this position, as we rotate, the satellite doesn't look like it's moved from where it was when it was over here, right? Now, let me ask you, are these two velocities the same? Am I traveling at the same speed as this satellite?
Yes. So
yes, intuitively it would make sense, right? We're traveling. This satellite is traveling with me. To me, if I ignore the stars, everything looks like it's in the same position, right? And for that to occur, it makes sense that it has to travel the same distance. But in reality, that's not exactly what's happening, right? So look at the distance that we're traveling. I'm traveling this distance, and then over here, this satellite is traveling this distance, right? I'm sorry for the colors. I have to get my markers, right? And so what's the distances of these two? Well, the arc length of a circle is just the radius or the distance from the center times r, right? So over here, this would be RE, and then up here, it would be RE plus this height. Times theta, right? So from this, it's quite obvious. Are we traveling the same distance in the same amount of time?
No.
No, right? Even though it looks like we're not moving, even though the satellite looks like it's not moving relative to us, it's traveling a different distance. So this velocity up here is greater. This tangential velocity is greater than if I was on Earth, right? Because the distance is greater. But what is the same is how we sweep through this angle. This is the angular velocity. And we'll come back to this when we do angular motion, but I'm going to introduce it right now. So the angular velocity is given by this symbol that looks like a W. It's an omega, a small omega. And this is equal to the change in angle over the change in time. And our angular velocities are the same. That's why it looks like it doesn't move. We rotate through the angle the same amount in the same amount of time. But because r is different, our tangential velocities are different, right? And the tangential velocity is related by omega times r. That's our tangential velocity, is omega times r. Now, because of this, right, we're traveling at a different speed. So if we want to travel in geosynchronicity to objects on the Earth, we have to travel at the same angular velocity, right? So that means that omega 1 or omega p is equal to omega s, where s is satellite and p is person, right? We would have to have this, right? And then we would travel with the object to Earth. Because of this, we have to satisfy this. Not only do we have to satisfy this, where if we, let's convert it, I'll explicitly write this out. So omega p is just equal to r vp divided by r, and then it's the radius of the Earth, so it's re, right? And this has to satisfy the tangential velocity of the satellite, vs, divided by the height. We have to have this for the speed of the satellite. We have to satisfy this, and we have to satisfy the centripetal acceleration question, the centripetal acceleration formula, right? So we have to have not only this, but we need to have the force equal to force of gravity equal to s over, right? We have to satisfy this as well, right? So trying to satisfy both of these equations, what we will end up finding, which we'll do right now, is that there's only one particular h where this occurs at, right? Its velocity can only be one value, which is given by here, right? And this will only occur at a certain height, right? To satisfy centripetal acceleration. Right? So let's determine this height. Let's see how high we have to go, right? So let's find out the velocity of let's find out what the velocity is first, right? So what did we say that our velocity was on Earth? So our velocity on Earth so VP on Earth is just what? We had it 2 pi RE, right, divided by a day, which is 1 day. And then we could transfer it into, and then in seconds, if you remember, we had right, so we know VP, right? So let's solve for our VS in this case. So it would be VP. Just bring this over to the R of the second. All right. We have VS over here, right? And this is the height. Now what we'll do is we'll plug this into this formula. Right? So FG is equal to G times ME over MS And then this would be divided by r squared. This is r squared. We would have RE plus H squared, right? And this is equal to MS. And then I'll put it in terms of V in terms of VP. VP squared over okay? Is everybody okay with this? Right? I just basically took this, and plugged it into here, and I used the force due to gravity as this, right? And let's simplify. We find that the two m's cancel out, so it doesn't matter about the mass of the satellite into this problem, right? And then we have a whole bunch of RE's, the radius of the Earth plus h, so some of these cancel out. These two cancel out, and then we can bring it over to the other side. So, well, we'll bring this over to that side. So what we end up getting and then I'll bring VP to the other side, and what we end up getting is RE H cubed. And what we get for this, we'll solve for this first. So we end up getting REH. We just take the cubed root of this. And we get this distance. Sorry. And we get this distance. About 42 million meters, right? And this is from the center of the Earth. So then H would be minus and then if somebody wants to calculate that. To the 6. And we find that H is roughly equal to okay, no, that's right. So then we find that H is roughly about 36,000 kilometers above our heads. So. $36,000 kilometers above our heads. And if we wanted to calculate the velocity of V, we can do that now. So if we just plug in these numbers into here, we find that Vs is equal to 3,770 meters per second. So we have to travel this fast. Okay. So I'm going to finish this chapter here. Please read at home the rest of section 4.6, weightlessness, it's called. And please look over Kepler's laws and Newton's synthesis, and explains how they calculated, how they got gravitational forces from Kepler's laws. And then read up on the gravitational field and the types of forces in nature. And so read the rest of the chapter, although it won't be on the test. So let's move on to the next chapter, work and energy.
So I'm so sorry. Are we moving to chapter 6?
We're done with chapter 6. We're doing, oh, I never erased this. This should be 6.
Mm-hmm. So we're moving to 7 right now.
Yes, we're going to move to 7.
Okay.
Give me 10 minutes, and then we'll finish the rest of the class. Yeah. I need a second. So I'll restart the room in 10 minutes. Okay. Bye.